Here we're told that a model for a data set is the equation y equals 2.3x plus 4.1. And we're asked to find the instantaneous rate of change when the input is x equals 1. If this at first seems obvious what the answer might be, then good, because you are looking at a linear function. So this guy actually has a vertical intercept at 4.1 and then a slope of 2.3. So it's going to look something like this, and you might just say, well, hey, regardless of what x you're at, isn't the slope always 2.3? And the answer is yes. Kind of answering part B already. But this is to kind of settle you back into the idea that instantaneous rate of change is nothing fancy, and it's really particularly only useful when you're dealing with nonlinear functions and you're trying to get a better approximation of what's happening when data might be increasing at a nonlinear rate. So we can apply the same idea though just to prove to ourselves that hey, this idea of instantaneous rate of change should still work for a linear function. So what we're going to go ahead and do is we're just going to, again as usual, pick our h's, and then we're going to look at our input values and see what those have to be. So we typically pick negative 0.5 and 0.5, and negative 0.1 and positive 0.1, and then negative 0.01 and positive 0.01. And then of course we have our input of interest, which is x equals 1. So we're going to have, let's see, that means 0.99, 0.99. We're going to have 0.9, and we're going to have 0.5 on this side, and then plus 0.01 would put us at 1.01, and 1.1, and 1.5. Okay, so these are the inputs that we're going to be comparing. Now, just as usual, we're going to compare every one of these points to our point of interest, where we actually want to know the slope. And we can, as always, choose to go ahead and put this into our y equals screen, and we'll do 2.3x plus 4.1. We'll come back and we'll do our bars, y bars, function. Oops. I'm going to put parentheses, so I'll do parentheses vars, y bars, function, y1, and I want to do y1 of 1, so the output when the input is equal to 1 minus the output when the input is 0.5, so I'm kind of jumping back and doing this one here, divided by the change in the input, which is really just a half, and I'll just write 1 minus 0.5 to represent that. Okay, well, not surprisingly, that rate of change is 2.3. So the rate of change between any 2 points on a line should always be that constant rate of change. So would this be any different if I picked 0.9? And you probably know the answer already. It's going to be 2.3. And then if I changed that to 0.99, 0.99 and 0.99, and I hit enter, well, there it is again, 2.3. And if you did compare the input of 1 to 1.01, you're going to get 2.3. And if you compared 1 to 1.1, change in output over change in the inputs, you'd get 2.3. And here 2.3 also. So what do you conclude happens at x equals 1? Well, obviously, since these aren't changing, your rate of change is fixed, and rate of change must equal 2.3. So explain why it was unnecessary to do any work for this particular function, because we recognize this as a linear equation in slope-intercept form, and we can just look at it and see what our slope is.